Let's discuss today a theorem on remainders. This remains one of the most basic lessons in elementary number theory, and as I've already told you that I shall take the help of the book to make sure that get through all the important ideas. It is very important to be guided by a good book, and I definitely want you to keep referring to this book. What is this theorem on remainders? So let's just first state it, and then of course we'll try to do a few problems from the book. So what this says is, first of all, let's understand what you mean by a remainder. Now, so let's say that I divide some integer by another integer, and when we divide 7 by 2, we know that the remainder is 1. So that is what typically you can expect. And what are the possible remainders when you divide by 2? The remainders could be 0 or 1. Similarly, if you divide by 3, the remainders can be 0, 1 or 2 if you divide by 3. Right? So now what happens after you actually carry out the division process? You can express 7 as the quotient times the divisor, in this case it's 2, plus the remainder. So in this case 1. Now this is written in the general form as, if A is divided by B, then A can be expressed as the quotient times the divisor, in this case B, plus the remainder. And this is a theorem that tells us about one way of computing remainders very easily. Now it is very obvious that if the remainder is 0, then definitely we can say that B divides A if the remainder is 0. So with this background, let us take the theorem that we are going to use today to solve a few interesting problems. So the theorem essentially says that you can add, subtract and multiply the remainders. So I just explain this with one simple example. In this example, I'm going to divide by 10, but that is only for convenience. There's nothing special about 10. You can divide by any number that you wish to in this theorem. So let's say we have two numbers, 14 and 27. Now 14 gives a remainder of 4 and 27 gives a remainder of 7 when you divide by 10. And suppose that we are interested in combinations of 14 and 27, like if you add them. Now the theorem says that you can actually directly add the remainders. So in this case, I can simply do 4 plus 7, which happens to be 11. And 11 should be considered as 1 because we are dividing by 10. So we conclude that the remainder is going to be 1. And indeed, you can see that 14 plus 27 is 41. And 41 leaves a remainder of 1 when you divide by 10. So this is what you mean by add and subtract. What happens if you multiply? And once again, the rule says that if you multiply the two numbers, then, and if you want to know the remainder when 14 multiplied by 27 is divided by 10, you might as well directly multiply the remainders. In this case, it is 28, and 28 should be considered as 8 when you divide by 10. Now, what happens if you actually multiply 14 into 27? I think you get 378, and this leaves the remainder of 8 when you divide by 10. So clearly, you can also multiply the remainders. So what is the proof of this theorem? It's actually quite simple. You'll be able to find it in the book. Instead, let us solve some few interesting problems with this idea that you can directly add, subtract and multiply remainders. And first example, I shall take from the book. It's on page number 25. So please go to page 25 and problem number page 25, problem number 15. And the problem says that what is the remainder? What is the remainder when you divide 1989 multiplied by 1990 multiplied by 1991 plus 1992 cube when you divide by 7. What is the remainder of this number to the right when you divide by 7? And as you can see that this is a huge number to the right, and what is the remainder when you divide by 7 can be easily found out by the rule that we just learned. So let us try to focus on what is the remainder of 1989 when you divide by 7. So let's actually divide 1989 by 7, and you can see that you will get something like this, and this leaves a remainder of 1 when you divide by 7, and the quotient is 284. We are not interested in the quotient. So the remainder of this number when you divide by 7 is 1. And now one quickly concludes that the remainder of 1990 when you divide by 7 is 2 and 1991 is 3. Now the theorem says that instead of multiplying the numbers, you can actually multiply the remainders. So we multiply 2 into 3 to get the remainder of this number divided by 7. Now here we have a plus, so we are going to add the remainder, and for 1992 the remainder is 3. For 1991 if the remainder is 3, 1992 is going to be 4, but it is a cube, so we should multiply 4 3 times. So this is the remainder when this number to the right is divided by 7. So this is nothing but 6 plus, now let's deal with this. 4 into 4 is 16, but 16 when you divide by 7 leaves the remainder of 2. So this is actually 2, and we continue to multiply with 4. 2 into 4 is 8, and 8 is nothing but 1 when you divide by 7. So the remainder of this number when you divide by 7 is 1. So the total remainder is 6 plus 1, which is 7, and this should be considered as 0 because we are dividing by 7. So 7 corresponds to a remainder of 0 when you divide by 7. So in the end, we got the answer to this question, that the remainder of this number when you divide by 7 is actually 0, and that means that this number to the right is divisible by 7. So I hope that this is a nice simple example that tells us clearly how the theorem comes into play. So let us continue with a few more problems. The next problem says that what is the remainder when 9 raised to 100 is divided by 8? So I hope you got the question. What is the remainder when 9 raised to 100 is divided by 8? Now 9 raised to 100 is nothing but 9 into 9 into 9 100 times. Now the theorem says that you can directly multiply the remainders. The remainder of 9 when you divide by 8 is 1. So this is just 1 into 1 into 1 into 100 times, and this is then 1. So we conclude that remainder of 9 raised to 100 when you divide by 8 is 1. There is a way of saying this. We'll learn this language in the next class, but I hope that you followed this problem and how the theorem was used in this problem. Let us continue with 1 or 2 more problems to consolidate this idea. The next problem is on the next page. It says that what is the last digit of 1989 raised to 1989. Let us first interpret the meaning of this problem. The last digit is always the remainder of the number when you divide by 10. So essentially it is asking you to find the remainder of this number when you divide by 10. So this number 1989 raised to 1989 is nothing but 1989 multiplied by 1989 multiplied by 1989 times. Now we can multiply the remainders directly, and you can see that the remainder of this number when you divide by 10 is 9. So this is nothing but 9 into 9 into 9 into 9 into 9, 1989 times. Now we make another interesting observation. Let us say that I pair these two numbers and I pair these two numbers. Let's see what happens. 9 into 9 is 81. 81 leaves a remainder of 1 when you divide by 10. And this also leaves a remainder of 1, and you can multiply the remainder. So it is 1 into 1 into 1. How many times? Okay, let me just divide 1988 by 2. How much is this? 2 9s are 18, 2 9s are 18, 2. So 994 times. 994 times. But we'll still have 1 9 left over into 9. So 1 into 1 into 1 into 1, 994 times, but since 1989 is an odd number, we have 1 9 left after pairing it up, after making 994 pairs. So 1 9 left, we leave it as 9. But now the answer clearly is 1 into 1 into 1 into 1 into 9, which is 9. So the remainder of 1989 raised to 1989 when you divide by 10 is 9, and therefore the last digit is 9. I hope you understood this problem and the simple trick of pairing, and we pair it because we get a nice number which is 1, and 1 is an easy number to multiply as many times as you like. So this is the end of this problem. Now let me solve two more problems before we end today's lesson. The next problem says find the remainder of. It is very much similar to this problem, but I thought that this is an idea worth repeating. So the next problem says, what is the remainder of 2 raised to 50 when you divide by 3? So repeat, what is the remainder of 2 raised to 50 when you divide by 3? And here also we will use a very similar trick. 2 raised to 50 is the same as 2 into 2 into 2 into 2 50 times. Now this also, it helps to pair it up. Now 2 into 2 is 4, and 4 leaves a remainder of 1 when you divide by 3. So the remainder of 2 into 2 is 1, this 2 into 2 is also 1, so you can keep multiplying 1, and since we have paired it up, this is 25 times, and this is nothing but 1. And therefore we conclude that the remainder of 2 raised to 50 when you divide by 3 is 1, and mind you, we've used the theorem that we learned today. So let us do one last problem for today, and this one I'll do a little bit slowly because it will be just a little bit more careful. But it is the same idea and the same way of dealing with the problem. So let me just do this one. This is the last problem for today. It says that find the remainder of 3 raised to 1989 when you divide by 7. Find the remainder of this when you divide by 7. So let us slow down a bit. This is the last problem for today. I just want to do this in an organized way. So basically, what is 3 raised to 1989? This is nothing but 3 into 3 into 3 into 3 1989 times. Now, the essential idea is already been conveyed. Is there a grouping? Is there a grouping that is going to help us? Now, you can see here that 3 into 3 is 9 and 9 is definitely not going to help. What we really are hoping is that we can try to make a group which will give 1. So let's keep following up this hope. So what is the remainder? Let's make a neat table here. What is the remainder when this is 1989 times. Okay, so I make a nice table here. What is the remainder of 3 when you divide by 7? The answer is 3. What's the remainder of 3 square when you divide by 7? And the answer is 2. What is the remainder of 3 cube when you divide by 7? Now here I'll use a simple trick. 3 cube is nothing but 3 square into 3, and the remainder of 3 square is already here. It's 2. So 3 square is nothing but 2 into 3. 2 into 3 is 6 because you're allowed to directly multiply the remainders. So the remainder of 3 cube when you divide by 7 is 6. And I'm going to continue for some time because I'm actually looking for 1 to appear here. So let me try 3 raised to 4, and I'll use the same trick that I used previously. 3 raised to 4 is nothing but 3 cube into 3. The remainder of 3 cube is already here, so let me make use of it. It's 6 into 3, which is 18, but we are dividing by 7, so that is nothing but 4. So I continue for some more time. Let me try 3 raised to 5, and I use the same trick again. 3 raised to 5 is nothing but 3 raised to 4 multiplied by 3, but 3 raised to 4 is 4. So that is 4 into 3, and this is nothing but 5 when you divide by 7. So the remainder of 3 raised to 5 when you divide by 7 is 5. And let me try one last one, which is 3 raised to 6, which is the same as 3 raised to 5 into 3. And 3 raised to 5 leaves a remainder of 5. So this is nothing but 5 into 3. And here you can see that 5 into 3 when you divide by 7 leaves a remainder of 1. So that's the magic number we are looking for. The remainder of 3 raised to 6 when you divide by 7 is 1. So now what is very clear is that if you make groups of 6, it will suit us very well, because this is 3 raised to 6, and 3 raised to 6 leaves a remainder of 1 when you divide by 7. So we will make 1989 into groups of 6. How will we do that? So let's actually divide 1989 by 6, and we get quotient of how much? 3, 3, 1. So 1989 is nothing but 3, 3, 1 multiplied by 6, which is actually 1986 plus a remainder of 3. So this is the main idea. 1989 has been split up into groups of 6. It forms 331 groups, each of which leaves a remainder of 1. And this 331 is not so important. What is important is what is left over, and what is left over is 3. So let me just summarize what we just found out. What we are essentially saying is that 3 raised to 1989 is nothing but 3 raised to 1986 multiplied by 3 cube, and 3 raised to 1986 is a perfect groups of 6. So when you divide by 7, this leaves a remainder of 1 multiplied by the remainder of 3 cube when you divide by 7, and this, you can look up the table here. The remainder of 3 cube when you divide by 7 is 6, and the end answer therefore is 6. So the remainder of 3 raised to 1989 when you divide by 7 is therefore equal to 6. I hope you followed all the steps in this problem. Tomorrow we are going to do 2 more problems to consolidate this idea. But meanwhile, please go through this chapter and also the book, and I'm sure that you'll pick up this important idea on remainders. All the best.